Good evening, everyone. Thanks a lot for everybody to joining to the session slash bootcamp on battery materials to digital twins. Skills for a career in next generation automotive and energy storage. I'm Suraj. I'm the founder and CEO of Decibels Lab. Very pleasure to be here in this session today. I'm the person supporting with my team to develop all of these courses, curriculums, and all of these things to create engineers for need for the sector in automotive, also for energy storage. With that as a quick note, let's not brag too much about what we do at Decibels. I think you would gradually know it, or by the virtue of searching it, you will really realize what we do at Decibels Lab. Maybe I'll try to take a minute at the last to explain about it. So as the important thing is to focus on the topic today and keep it all going. The first and foremost thing is that what's the trend and opportunities? You want to be here today in this webinar. Tomorrow, you may have to want to work in the industry of what we're talking about, or somebody who's already there in the industry, they want to go maybe up the ladder where they would like to gain more exposure and more skill sets. Or even there is somebody who's fully fresh, they may want to build their career in the areas of maybe the energy storage sector or an automotive EV sector, right? So if we sort of broadly understand, and the importance of this slide is that, hey, what industry are we trying to talk about? What is that sector is doing right now, and what is the direction of that sector in the next few years, so that if I get that skill today, if I have that competency today, can I get a good job? Can I get a good, upgrade in my job and things like that? Or can I even work in the areas of research that would again lead into the areas of employment or anything else? If you broadly see today, in terms of the India's acceleration towards adopting to the energy storage, you see a very significant growth that Indian context have taken it up. The image in the left and bottom corner, if I slightly zoom it out for you, is that there's a huge amount of tendering that has been offered by the Indian context to adopt, to improve the sectors of energy storage. We do see that mostly that is filled by certain sources of the energy, but there will be a lot of input and demand for the requirements through the energy storage as an adoption. That means the sector as a government is looking forward to invest and heavily and steadily in the areas of energy storage. And today, the requirement for energy storage sector itself has grown very heavily, and we see that a lot of battery suppliers, companies around the ecosystem of battery pack manufacturing has been focusing on developing solutions also for the energy storage. I've heard from my friend is that there is a demand more in the energy storage sector for the lithium-ion cells than even the automotive sector today. That means there is a lot of traction happening in that areas of the sector. So we will talk about it, what exactly this business as a demand will lead to a technology, and then that lead to the job market and the requirements of talents in that sector. The same way, if you see in the mid section here, is that the energy consumption in the global market is also growing very heavily. And we keep consuming more and more of energy every year. And that needs to be buffered in some way. And today, I think all across developed countries, we have the ecosystem of hybrid energy storage. So you have the solar, you have the wind, and then you have the nuclear, thermal, and all of that. And there is a buffer of energy that is being managed by the BESS at a megawatt or gigawatt scales today. And we have been interacting with some of the participants from that sector as well, which I will talk about in the next few slides. And where is the battery coming in between? Is right now you see in the right-hand bottom corner is that the battery is fitting somewhere in between the source of energy production and the source of energy consumption. At a BESS, at a very large scale or a megawatt or gigawatt scale applications, you see companies like Tesla, who is setting up a very large energy storage sections. You see companies like Fluence, which is part of Siemens, BYD, Cattle, all of those companies are setting up a huge scale of energy storage solutions, right? So if there is any required output from the excessive output from the solar or the wind, they get stored in the battery, and then whenever there is a demand, it gets shelved off from that batteries to the end usage. Right now, we see the end usage would be a house or even the vehicle. So all of that becomes a requirement at the source, and then even some of the houses are producing energy. So you have the grid balancing happening, or the houses producing the energy back into the grid. So you need to kind of find a way to have a solution that can balance out your requirements, because sometimes you have a peak requirements, sometimes you do not have, sometimes you have the source of energy which is at a lower cost. And at a time when there's a huge energy demand, you can pump in the output from those sources. So in this way, the battery is becoming a key element in the complete energy storage sector, where you have an option of optimizing your cost, optimizing your storage, and also making it much more greener and viable for the sustainability requirements in place. So that's the broad idea of what we're trying to transition. And with all of these things, we see there's a huge stress for energy storage to become transition towards clean energy, right? And that's where you require, we don't still fully say the battery is completely green, because there is materials and all of that goes to an extraction process, and then finally you need to make a cell. There is a manufacturing emissions that is going to happen, but if you compare that with a coal or another source of energy, you will have some kind of a competitive advantage to take care of it. So keeping that part of the emissions produced in the manufacturing, but the application perspective, there will be a lot of advantages to use cell as a requirement to transition towards a clean energy. With these contexts, there's a huge demand as a business, and then this business as a demand will lead to the technology, right? Because if you're trying to buy a laptop, somebody's going to manufacture a laptop. So they need to have a technology to manufacture. The same way, if the business demands, if the India would like to consume a 10 gigawatt or 10 terawatt of energy, then you have to produce it somewhere, right? To supply to the required destinations in place. And then you would have a technology. So it's not that the battery is the only technology. And the same way, if you want to manufacture an electric vehicle, or if you want to develop an electric vehicle, you want to have the batteries as a primary source of energy. So end of the day, that comes back to what is a viable solution technology, right? That's definitely today, with whatever we have, it is lithium ion because of its energy density and a lot of other factors. So now, yes, there is a solution that is available as a technology, and now it goes through certain things, right? So it has the complete value chain. What is a value chain that we go through? The first is the materials, and then forming a cell. Now, from the materials we have, we form the cell, and from the cells that we have, we build a module. From the module, we're going to build a pack, and then finally, we're going to integrate that pack, maybe with a battery management system, maybe with an IoT, maybe with the charger, all of that other things that will come across. So in this slide, we are just talking about specifically focused on things on materials and a cell, right? So if you want to make a battery, you need a materials. And these materials are in a very different stage when they are available. So somebody need to dig the earth, extract, or maybe have to do it with the different processes that is available today. Like how we have lithium brine. So you take the water and you let the water evaporate, like how we make the soil. So you take it out and then you extract lithium out of it with the lithium brine. Or you dig the earth and find specific components, and then you refine them to get a final lithium. The same way, the battery is not just lithium, right? So you may use just like 4, 5, 6% of lithium, depending upon different battery chemistries. But when it comes to other materials, which are more predominantly also used, are copper, because your current collectors are made up of copper. You have the nickel, manganese, cobalt, titanium, if it is the phosphate, LFE-based chemistries. Aluminum is also going to be current collector. You have a graphite, which is basically for your anode. Majorly, 99% of the materials today made in lithium-ion cells have a graphite as a negative electrode. And then silicon, which has been an exploratory option, also been commercially available in some of the cells where we have doped the silicon to increase the ability of the storage of energy density. So all of these materials are ready to be extracted at the primary source. When you get lithium or any other metal, if you want to manufacture a cell, there are a lot of other many processes to make it to a compostable anode material or a cathode material or a separator or an electrolyte, all of this, right? So that means that requires another all engineering together. And it means it requires somebody who have the knowledge of material science and developing materials at a lab scale and then taking that materials from the lab scale to the large volume scales as well. Because you would have a lot of challenges when you want to manufacture something at a very large scale. So we shift from the left of the screen, which is where we have a material that is the companies who are very well defined and evolved in extracting materials, processing the materials, and they come and they bring those materials and give it to a company which may want to make a cell. And there is a role of an engineer who is a material scientist who will work through all permutations and combinations to think through a process to arrive at combination of materials to form the cell. If you have come across something like NMC 811, right? So there's a composition of 811. So similar way, if you want to arrive to that, how do you talk about a lot of materials intrinsic properties? Because these cells are going to work at different chemical environments. They're going to work at different temperatures and a lot of vibration. Then the cells are going to be operated for different charge cycles, different discharge cycles. So when you go through all of these things, how do you expect these materials to behave, right, inside the cell? So with all of those intricate complications in place, we need engineers who really have a knowledge of material science, who work on evolving, making a raw material into the anode materials, into the cathode materials, or into electrolytes and separators. That forms one side of the value chain. And in addition to that, we are evolving every day to make different type of cells, right? Our chemistry of cells. So within lithium, we are exploring options to make solid electrolytes, right? And we are exploring options to make sodium-ion batteries. So much of evolution that happens around in the battery technology. And that means we need a lot of engineers who have the knowledge of electrochemistry, battery materials, and then all of that. Then once all of that is figured out, we come to a process for the mass manufacturing, where we have several and hundreds of processes where we talk about in this right side of the image, which is slurry preparation or a coating and drying, the calendaring, cutting the electrodes, cell assembly, finally filling the electrolyte. So which is a whole of a production process that happens at a big manufacturing plant where somebody would like to manufacture a cell, right? So once all of that happens, we will have a cell. So it's a job of a manufacturing industry to manufacture a cell, and a material industry to explore materials and then bring out a new material from a new material. Finally, okay, the Tata has made a cell, or Tesla has made a cell, or whoever has made a cell. You need to engineer that cell for a specific application, and that's an application engineering altogether. So what happens in that value chain of application engineering, right? So it's not that all the cells that is available in the market will suit your application, right? It may be chemistry, it may be the energy density, it may be the ability of the cells to undergo charging rates and discharging rates, ability of the cells to withhold temperature limitations, longevity of the cell, and the type of the cell. It's an energy dense cell or a power dense cells and things like that. There are hundreds of varieties of cells, hundreds of varieties of cell manufacturers are available. But how do you come to know whether this cell suits to my application, right? I'm going to make a bike. I'm going to make a car. I'm going to make a truck or whatever it is, or I'm going to make a battery pack for the energy storage application. How do you come to choose, okay, this is the manufacturer, this is a cell, and this is the right suitable cell for my application, right? So that is what happens in the further part of the value chain, where we talk about choosing cells, testing them, characterizing them, finding them whether they meet our application requirements, then integrating them to form a module, and then to form a pack, and then finally doing all of that, testings of integration of all your software, BMS, and everything in place. Also the electrical integration, mechanical integration, and finally you make a product that goes into the market, right? So we started at a materials as a requirement, and then we passed through the journey for a cell, then making a module, pack, and all through the integration. I am trying to stress on some points where we try to take those words and then use them in the further slides of the presentation. So when I spoke about, let's say there is a cell, right? Somebody has made it. Can I test hundreds of cells from hundreds of suppliers? That's like 100 multiplied by 100, right? So that's a lot of cells which I have to test. If I have to test them for all given conditions, because my vehicle is going to operate at 10 degrees, 20 degrees, 35 degrees, 45 degrees, somebody's going to drive in different ways. If I want to test such a cell, hundreds of them at my lab, which is going to take a lot of time and money, right? Let's just park this topic for now, and then we'll talk about it in the further part of our webinar or a bootcamp, that where we leverage technologies of digital twinning and all of those things to reduce the time that I would take from the part of the cell to the pack. The same way, when we are trying to choose material, like you're trying to form a material, right? So which is an anode material, cathode materials. And after you form it, you build a cell, right? You develop a new electrolyte, you develop a new separator materials, and all of that beautiful things. But if you want to make sure that is okay for an application before you go through a long manufacturing production line, you need to ensure that this is okay for the application, right? So 100% there is a physical testing, okay? There is a physical testing. That means you form a cell, you form the half cell, you form the material, like you do a lot of analysis and everything, but it is very time consuming and it's very expensive processes, right? How about we can have a simulation tools that can do computations at that level and help you to see if I blend two materials, blend 4-5 materials, how it's going to behave, right? So which is going to save a lot of time and money for the researcher to work about it and say, okay, hey, maybe out of my 25 combination of materials, this one will possibly be a right direction, right? So rather than making 25 materials and then figuring it out, hey, this may not work, the amount of time and money that you spend, and on top of it, because there are competitive companies who also want to bring a cell into the market, right? So there are a lot of efforts which helps in creating these cells, a lot of efforts done by softwares in creating the cell to an applicability suitable to the application in place. So we'll talk about that few points in the further part of the journey. Any questions from anyone till the slide? Quickly, if you would like to take a minute for the questions. You have the option to unmute and ask a question in case you have any questions. All right. So if no questions, we will move on. Okay. So let's just talk about the battery materials. I try to connect this to a problem statements that we see in the industry today. Is that today maybe it is true that in India we have found some of the places where we can, extract a lithium ore, right? So it is also very concerning that do we have an enough capable technology to refine that ore and finally extract a lithium as a material, right? The point number two, once we extract those materials and form lithium, uh, how much of our core technology or competency or IP is available with us today to derive those into the complete material as an anode materials or a cathode materials, right? Finally, the all of this is sorted out, and then we have the supply chain limitations in terms of the cost, because you can make something at a lab level, but to manufacturing at a scale, what is the supply chain limitations that comes into a picture within the ecosystem that we currently have? And then all of that, what is available technology with us to manufacture cells from nothing as a raw material and then completely as a final cell that comes out in the production line, right? On top of all these things, there is an ever-changing technology. If I invest today to manufacture NMC and X variety of cells, but in another 1 year or 6 months, maybe cattle or BYD will come with the better chemistry, right? How quickly, how evolved are we able to realize that the investments that we have done today is going to be a viable solution for the market? And I will be very competitive in cost and technology that I'm quite well against the very established supply chain that is available today, right? So with that kind of things, what do we need at a deep level is that the people who have the capability, exposure, experience to work with that kind of materials, the kind of technology, so that we will be able to take care of these things. Uh, if you're aware about it, that close about 99% of anode materials and cathode materials comes from China today. We may manufacture a battery in any country, name it as in India or anywhere else, but the material that you need to make the cell today comes from somewhere else. If that the whole supply chain dependency is there, one part of it's that, and then how much of that is available today with us to manufacture within the ecosystem as a country today, right? So when we realized all of this, I'm talking about a problem statement, but I'm trying to come to a solution as well in the end of the session. When we talk about what is lacking today, and then how do we address that? And there comes the requirement of developing something, right? As something as a cell, for sure. Nothing apart from it as what we're focusing on today. So it has to go through very well-defined processes. When we talk about the prototyping a cell, we talk about developing the cells at a lab scale, maybe a coin cell or a small pouch cells level. And then we talk about all the characterization methodologies when we talk about various XRDs or SEMs or variety of characterization procedures, but also where we perform tests such as EIS or GITT or maybe even HPVC or variety of those tests in place. So to give a quick overview as an importance of these things in terms of the processes, in terms of the characterizations, or also importance of these tests. So we have one of our technical consultant, Dr. Manjunath C. So if you're there in the session, so I would request you to have a few, throw a few glimpses about how this whole process of, material to a cell at a lab scale, you have all of that experience developing it. So kindly give us a quick overview about that process, please.
Okay, hi everyone. Am I audible?
Yes, you're audible, sir.
Yes, as Suraj has explained detailed about the battery components, right? So the battery is basically made up of four components: anode, cathode, electrolyte, and separator. So first we start with the material. Then after optimizing the material, uh, we go for electrodes. So before going for electrodes, we have to confirm the crystal structure, suitability of those materials, particle size, etc., with various characterization tools like XRD. XRD is used to analyze the crystal structure, etc. Yeah. And scanning electron microscope to know the particle size, the composition, the purity of that. And we are also discussing about XPS, that is X-ray photoelectron spectroscopy technique. That is another technique used to know. For example, if you know NMC 811, it has lithium, nickel, manganese, and cobalt. So to know the exact composition, we use the SEM, EDS, and the XPS. So these are the techniques used to analyze the material characteristics before making the electrodes. So after manufacturing all these cathode materials and also the graphite, which is being used as anode in various battery chemistries. So that is the material part. So once we are familiar with that, then we go for electrode fabrications. So for that we use copper as a foil current collector for anode. So on the surface of that we coat graphite. So then for aluminum, for the cathode we take aluminum foil, and on which we coat various cathode materials. For example, if NMC battery, we coat NMC material. If it is LFP battery, we coat lithium ferrophosphate materials. So after coating that, we have to make sure that the coating is proper. So in addition to all these materials, we also add other additives like binders, solvents, etc. So during the fabrication of electrodes, it follows various stages. So that is also exclusively covered in this course. Various stages, electrode manufacturing and cell formation and cell finishing. So once we are done with that electrode fabrication, we have to go for testing. So whether that electrode is suitable, whether it is exhibiting the expected voltage or current capacity. So before fabricating the cell. So for that, we go for various electrochemical techniques like cyclic voltammetry, electrochemical impedance spectroscopy, and galvanostatic charge and discharge techniques. So cyclic voltammetric technique is the most common technique which is used to identify and whether this material can behave as anode or cathode. So, and it will give whether the material can undergo oxidation. Oxidation means it can give electrons, or reduction, whether it can accept electrons. So battery is basically consisting of the two electrodes, anode and cathode. During discharging, the anode has to give electron and cathode has to accept electron. During charging, it's vice versa. So that those characteristics can be understood by this CV technique before going for electrode manufacturing or cell fabrications. So that is the advantage of this technique, and we have discussed about in detail the principle, the methodology, and we have also compared the cyclic photomerogram, the spectra of various battery chemistries, including the anode graphite, or silicon graphite composite, or NMC or LFP, or other sodium ion batteries are also we compare in this course. And after that, we go for galvanostatic charge discharge technique. It is also called chronopotentiometry technique. So where we are going to study the how long the battery can hold the charges, means the current. By applying the current, the battery voltage increases, and we also study the current capacity, the capacity of the anode and cathode material. So how much charge it can hold. So based on that capacity values, they actually calculate how much quantity of anode, how much quantity of cathode active material has to be taken to manufacture the cell. So we discuss about the principle of this technique, the cycling stability, the number of charge and discharge cycles that material can withstand. And based on this GCD data, we can actually calculate the energy density, that is watt hour per kg, and the power density, the watt per kg, and also the Coulombic efficiency. So then we also, the very important technique is the electrochemical impedance spectroscopic technique. So in this, we actually study the kinetic parameters of the charge transfer. So basically, uh, the electron is being transferred between the electrode and from the current collector, and with lithium, and also the ions are being intercalated. For example, if you take the lithium ion battery, during charging, the lithium ion has to come out from the cathode and it has to intercalate into the graphite in the anode. So there are actually two phenomena here. One is the electron transfer, the other one is ion transfer. Ion transfer is called mass transfer. So it has to travel from one electrode to another electrode compartment, where it has to pass through the electrolyte separator, and then it has to move from liquid to solid, that electrode, so that it will experience various resistances. So that resistance can be understood by using this electrochemical impedance spectroscopy. So this is a very important technique, especially to monitor, to model the battery that we are going to study, the next part of this course. So we are going to explore the charge transfer kinetics, that is with respect to electrons, and the mass transfer kinetics, that is with respect to lithium ion. And we also calculate the lithium ion diffusion coefficient. It's a very important parameter that we use in simulation techniques. And RCT, the charge transfer resistance and Warburg resistance, all these resistances that we are going to study. It is also called impedance spectroscopy. Impedance is basically the combination of the capacitance and resistance. So we understand the percentage of the capacitive behavior and the percentage of resistance behavior of both anode and cathode. So based on that, we design the circuit and we understand what chemistry is happening inside the battery actually. So for example, if you take LFP battery and NMC battery, if you record EAS, obviously it get different because that battery chemistry is different. That resistance, the impedance experienced by those devices are completely different. If you use those batteries for about some 50 cycles, and then if you test EIS, so the spectrum that we get is completely different than the initial spectra. That will clearly indicate the degradation mechanism. So whether the electrode is getting degraded or electrolyte is getting degraded, whether thermal runaway is being started. So all those things can be understood by using this electrochemical impedance technique. This is a non-destructive technique actually. So without opening this battery, just by running, doing we can easily characterize the characteristics of the anode and cathode materials and the electrolyte life. All those things can be understood without opening this that device, the cell device. So this is a wonderful technique. Based after recording EAS, the next part will be the simulation part. So in addition to this, in this course, we have also covered the various advanced battery chemistries. For example, the future is solid state battery because of currently we are using the organic electrolyte based batteries that leads to thermal runaway because organic electrolyte are prone to catch the fire. So that's why they want to replace the organic electrolyte by the solid state ceramic electrolyte where they can withstand even 1000 degree also. So that also we have introduced. And we have also discussed about the sodium ion battery in this course. We have compared how the sodium ion battery is best and what are its advantages and disadvantages over lithium ion chemistries. And we have also discussed about the redox flow battery, that is for the grid storage application, just to give some glimpses. And in addition to advanced battery, we have explored the characterization techniques like, as I mentioned, XRD, SEM, and TEM, and XPS. This is with respect to electrode, material, and electrode. And with respect to electrochemical test, these CV, EIS, and GCD. So these things are actually very important. So having knowledge about the material properties, understanding the material structure by using the various characterization techniques, and understanding the electrochemical behavior by using all these three electrochemical techniques. That data is actually very, very important in order to design the digital model of this battery. Yes, Suresh, sir.
Yes, sir. Thanks a lot, sir. I think it kind of opens up another webinar topic in the upcoming future that maybe we will take each of that topics whole from the breaking up of our raw materials, and then maybe just starting to that stage of uh, anode or cathode material, and then the analysis type, and then forming it, and then performing all of this EIS, CV, and other things. We will look forward to host those webinars in the upcoming days. It'll be a short, quick 30 minutes on Saturdays. We'll be very happy to have you in the upcoming week session, sir. But thanks a lot for your time today to spare with us to give a quick, very quick glimpse of what is it that is about going through the journey of cells. Thank you.
Yeah, I would like to add one more sentence, sir. Actually, I have come across many, the courses, but this is a very, very unique course where we can find, starting from the basic chemistry to materials, materials to electrodes, and electrodes to cell and cell modules, then testing, characterization, and then combining with simulation models and digital twinning. So combining one course, I've not found anywhere. So I think those who take this course would definitely, it will definitely help them. And in addition to this course, we can also support them if anybody wants to continue their, as I keep telling, pursue the PhD in this technology. That also can come and serve during the.
Absolutely, that's
There is also possibilities there.
Yes.
So those who want to do PhD degree, if they can take up this course, that will definitely add a value to the PhD course.
Absolutely, sir. Absolutely. By the way, we're very glad to have you as a part of the course, sir, to help us in structuring this course from the perspective of materials to bring a quick few points before you leave. So, dear participants, Dr. Manjunath C is among the top 2% scientists in the world who work on specific areas of batteries. I would say materials and electrochemistry. Has published more than about, I think, 100 plus publications. Done one of the top layer journals in the materials sector. So in the upcoming sessions, I would love to have you as a part of the session. So where I would be very happy to get through more details of the section, and we will also love to have you, the participants here, if anybody is interested to take up any PhD in the very specific areas of materials, and also focus to electrochemistry. We have options open. If you are interested in discussing, yes, you can connect with our team. Mr. Vinayak will help you out with the further sections of engagement all together with you. So with that note, I think there is one question from Tejas. He would like to understand that how often are these characterization techniques in manufacturing, or is it used only in battery development? So if you would like to answer that question, please.
Okay, among this, the EAS can be, the electrochemical techniques can be used at cell level.
Right.
So once you have made the cell, we can use electrochemical impedance spectroscopy and run that cell for several cycles, charge and discharge, and we can keep studying the impedance behavior of that cell.
Right.
So that will help us understanding whether the electrode material is stable enough even after 100 cycle, or is there some degradation is happening. Those things can be understood by using EIS technique. However, that XRD cell and other techniques, that is at material level. So that to know in detail about the material, we have to open the cell and then study the behavior of that. So, but at the cell level, manufacturing level, even after manufacturing the cell, the lithium ion cell, we can definitely use electrochemical impedance spectroscopic technique. So that will help us in understanding the impedance behavior and the battery stability and other the electrochemical aspects.
Absolutely. Absolutely. So just to add on to the point, so mostly in the manufacturing, at a large scale manufacturing, we will possibly use an ACIR, which is done typically at a 1 kilohertz frequency. And we would use the cell testing machines, which is a cyclic machines, which can do complete charge and discharge, so they can identify capacity. And maybe for the internal resistance measurement, mostly we use either the voltage measurement, it is basic thing, and then the ACIR, which is a cut down version of EIS, but done at just one specific frequency, about 1 kilohertz at a given SOC and a temperature in place. And that's what we use in manufacturing mostly, if I could answer. So yeah, so with that, we will go ahead to the next points in the slide. Yes, so Vanessa, thanks a lot for your intervention to give us a good idea about the chemistry side of it, and also characterization on the testing, and also on the XRD and other things. Thank you.
Thank you, sir.
Thank you, sir.
It's a lot.
Thank you. So continuing our session, we focus more on the battery modeling, right? Now, what is this part in the battery modeling? The idea of this is holistically to incorporate the characteristics of the battery in a mathematical format, right? I have my teammate, Mr. Krishna, who will help you out with that. But before I go there, I just give a few glimpses of what is actually happening in the whole broad spectrum, because he would talk more technically in depth about what is it as in terms of the modeling, right? But I'm going to talk about more from the perspective of a business and a simplicity to use that in the different cases. So let's say we have a cell manufactured by the material scientists and the production house and all of that. My application is, let's say, a vehicle, right? I'm going to charge my car, I'm going to discharge my car however I want. I will operate my car in any temperature conditions, any terrain conditions, and all of that. So what I want to know is that I have 10 suppliers who will supply the cells. I want to know which cell is better, right? Which cell will behave well for my applications, because each cell has its own intrinsic pros and cons, right? So if I have to do that, I have to test, which I was talking to you about, many cells in my lab, and I will spend years and years of time, right? Somebody may ask me, why don't you ask a supplier to give you the data? But how well do you trust that data, right? Because anybody can give you data to make you convinced, because they want to sell their cells to you, right? So you have to gain your confidence to say, oh, hey, this is the right cell for me. So one, you spend a lot of time, years of time, money and everything in testing them. Finally, out of those 9 cells, you may choose only one cell, right? By then, there's a new chemistry of cells might have come into the market. Now, this is one complexity that happens with the battery industry for anyone and everyone. Let it be Tesla or let it be any other company in the world, right? So that is one side of it. And also, we use these models that we develop in variety of algorithms for our estimation activities, such as SOC, when we use the Kalman filters and things like that. So we can also use these models that is for developing your batteries. I can make a digital battery model, right? I can develop the model that will be talked to you by our team at Krishna. But let's say we have the model, but when you use the model, you can build a digital battery pack. You can see charging it, discharging it. You can check how much temperature will increase inside the battery without even developing the battery, right? Without even having a CAD model of the battery I'm talking about, right? Pure mathematical models. We can check how much will be the voltage drop because of the resistance across the battery, right? You can do your charge cycles and discharge cycles, check how the battery is going to behave, in various different conditions. So you can incorporate a lot of your non-linear, situations, right? And then tell this digital model to just go through that kind of a scenario and then say, this is how I will be ending up in next 6 months, 9 months, or 10 months of time. So this is at a very large scale, where we need these cells at models at a one level, and then to use it for an application. So we have our teammate, Mr. Krishna. So Krishna, over to you to just give us a quick glimpse of, hey, there are a few type of modeling, RC pair modeling, variety of RC pair, and then where we use them, and then just throw us a bit more light on the electrochemical model, for the good of it. So yeah, over to you, Krishna.
Yeah. Hi all. Yep. Like as Suraj was discussing, and as like Dr. Manjunath was mentioning, related to the data, right? So here, like as we talk about the battery modeling, we can divide the battery modeling into different kinds, like the mathematical, and there are something like the electrochemical, and also we call it as like black box modeling, which is like a third type. Yeah. So here, like as you see, if you see the slide on the pic, we can call it as like a mathematical modeling, like which has a physical meaning, where we can see some circuit kind of stuff. So like it's completely of the data, like how all these parameters which we see like R0, R1, C1, like we derive it through the testing itself. So as Dr. Manjunath was mentioning some of the testing methods, like HPCC test, or like whatever the DCIR related test. So those are some testing methods where we can draw our like these parameters, just making use of simple like Ohm's law approaches. And there are also the, when we talk about like electrochemical models, which is involves like more of physics inside it. So let's say like when we say the physical model, like it will involve, like it will consider all the properties of your the material. Let's say the electrode, electrolyte, uh, and other like how do you say, like current collectors, like all the properties, and we define the equations, like the flow of ions from one electrode to the other electrode, and electron from one to the other. So in this way we define the equations that what we see in the electrochemical models. So for that we need material level data. So when we say the application of those models, like right now they are just being used as simulations, but in industry what we see that they are going to be implemented at the BMS level also. Like right now, because of the computational requirement, they are not being used. We are just sticking up with the ECM models, like the one which was I saying that equivalent circuit models. But right now in the market, like they are focusing how to make use of these single particle models. This is just an example of the electrochemical model. So these can give like more accurate values, like in terms of estimations. So right now you can make use of these like in the fast charging technologies, like where you can like control your like the current tapering stuff. So in such way, like these models will come into help, and it can give the more insights at the material level. Yeah, these are some mathematical data where you need the information of your, like when we say like the physical. But there are some methods like black box modeling. We don't require any like we are not going to go for any building up the equations. Okay, so we will just make use of the input and output data. For example, like you kept the cell on the charger, on the cell cycler or in the vehicle, you just trying to like apply the current, like you're trying to discharge the charge, and you will note the current has an input. On the other side, your cell voltage is going to change, right? So that you consider it as output. So with input and output, you can bring up some machine learning models. So that is again like new stuff which is going to come in the market. Like right now, it has been implemented like in the most of the cases. Those are like all these information like related to the machine learning based models and also like electrochemical based models. So we can like come up with some hybrid stuff. So these all lead to the discertain developments. So yeah, there are some limitations in terms of development of all these, but like combining all these stuff, we can like reduce those. Yep. So sorry.
So go ahead.
Yep. So here, like when it comes to like development of these, we can like make use of like MATLAB and the Python and the console. But I recommend like there is something a module called PyBum where you can look into it, where it talks more about the electrochemical models for the development. Yeah. So I'll just quickly give some more points. Yep. On the MATLAB stuff. So you can find some more modules in the MATLAB related to the electrochemical models. Yeah.
Right.
Hey, so yeah, you can take it. Yeah.
Sure. Krishna. Thanks a lot for throwing the light on different types of modeling. Can be an equivalent circuit-based model, which we can create with the help of HPC data, or we can also, get some improved models with the help of electrochemical modeling. So for somebody who might have not thought what is this models are, because I used to feel the same way. Hey, what people really talk about just as this models, right? If you think that it's a pure representation of a real component, imagine there's a cell, you charge the cell, what happens inside the cell? The voltage increases, and then the temperature increases, like its internal resistance changes, a lot of these things, right? Imagine you can recreate a mathematical functions for this and try to develop them with the help of mathematical tools. So you can call them as models, right? At the one simplistic level. The other one, because it is not just as simple as that, right? The cell is completely a nonlinear system. So there are a lot of things and influences which is actually making this thing happen and behave in the way it is behaving. So you can go to that very smallest particle size, and then you can recreate that in the software. The problem is that now for a per square millimeter of a space, you may have millions of those particles, right? Your system need to be computing all of those particles moving in, moving out through an electrolyte, its own interfaces and all of that. Then the model becomes too complex and then too heavy to run on a simple microcontroller. So people are developing them and then we use them, but we would like to study more in depth at the smallest level. Then you can go for the electrochemical modeling, right, Krishna, if I understand it correctly. Then if you want it at a very simplistic level as a representation of the cell, so we can stick it at the equivalent circuit models, which are today implementable at a microcontroller level. Yeah. So great. With that note, what Krishna has left is I take you that, okay, we have the chemistry, we have the material, we have the cell, we do the manufacturing, then we got the way to develop a mathematical model of the cell, right? Now, as we said, that the cells are non-linear in nature. You could use a lot of regression models and machine learning and AI and all these things combined together. So what I want to do as a digital twin, right? I see a one word called application here in this slide. I see that this cell can be used in vehicle, this cell can be used in energy storage, anything that is. So now I want to understand the possibility to use this cell for my application. Point number one. Point number two, let's say I decide that this is a cell I'm going to use. I don't know how it will behave in the real world because it is highly impossible. Let's say a company has sold 10 lakh bikes. Do you think all those 10 lakh bikes are driven in the same way, charged at the same time, driven in the same temperature, driven in the same road condition, driven with same one person on the road, no luggage? No. There are a lot of challenges with respect to its operation, right? It is not done in one way, right? It is not a lab. It is not like you charge the cell at 1C, discharge it, 1C, charge it, discharge it. If you do it 1,000 times, you would only get the behavior of that cell for that condition only, right? But in the battery pack, you have a combination of cells, combination of modules. So there are many cells and many modules in place, right? Imagine how the whole battery pack will behave. And at the end of it, what would be the life of this battery? How does the battery degrades over the time because of temperature differences, voltage differences, imbalance differences, charging at different temperatures, charging at different C rates, all of those things, that everything will lead to one thing called state of health or state of X, okay? Which is defined in this whole point, right? Which you see here, that because if the battery fails earlier than warranty period, the company has to replace that battery. It will be energy storage, it may be an electric vehicle or anything. You buy the vehicle, if the battery fails before this end of life, before this warranty, you're supposed to replace that battery, which becomes a very expensive element for the company. But how do we avoid it, right? You can do that where people are trying to do it, or have done that, I would say, with the help of digital twinning, okay? So what is a digital twin? Digital twin is just a replica of your real system. Imagine a car, you have a Tata Nexon or an Ather bike. There is a battery, right? You're charging the battery, discharging the battery, subject to different ambient temperatures and all of that. What are we measuring, right? We are measuring the voltages, we are measuring the temperature, we are measuring the current. Only these three things we are measuring. Nowadays, there are companies also trying to put an EIS in the BMS and then measure the resistance of the batteries directly. But anyway, let's just take now four. So voltage, temperature, current, and maybe the resistance if it is possible. And not any real BMSs today available with the EIS capabilities, but just let's assume that one, okay? Now you are collecting this data. This is done by your BMS, right? Then the BMS is actually calculating all of these things called SOC, SOH, doing cell balancing and all of that. Now the microcontroller, because in the car or in the bike or in the energy storage device, you just have a small microcontroller, right? Which may have a maximum of 5 MB storage or maybe a few KBs of RAM. It really cannot process these models which we can develop in the computers. So what companies are doing, they take the data of these things over the internet, because your vehicles are nowadays connected to the internet, right? The BMS collects all the data, brings the data, gives it to the IoT device. Now from the IoT device, you are able to collect and pump the data to the cloud. Okay, let's imagine this cloud is like an AWS or an Azure or anything. And in there, you will be able to run these models because these models are too big. These models are too heavy, right? It takes a lot of computational processing power and a computational power. So we can't do it on the the edge, because edge is just having a microcontroller, right? So you can run that model in here, and you can run all of your other things like machine learning and too many other things, whatever you want to do in the cloud, right? So in the vehicle level, we have a BMS. In the cloud level, we have a digital twin. Now, what we're trying to do with all of these things, right? So we're trying to understand how my battery is going to degrade. Imagine I see some patterns that the customer is trying to charge the battery. A simple case, okay? Every day at night, he comes to the home driving the bike at about 7 or 8 o'clock in the night. He keeps the battery for charging. Every day he does this charging process, okay? Because he does this charging process, what happens? The charging completes maybe at 8 o'clock to 12 o'clock in 3 hours, because he or she is charging every day, or maybe 4 hours of charge. So from the 1 o'clock or 12 o'clock till the morning 7 o'clock, the battery is in the idle condition, right? It is neither charging nor discharging. It is in the rest condition. So it may undergo a calendar caging, correct? Because of its rest condition. At times, when you drive the vehicle from your office to your home, the battery temperature is slightly higher. Example, right? If you charge the battery at that temperature, there is possibility that the battery life may get impacted. Or as I said, because of the calendar caging at night, it may get impacted. So now there are a lot of nonlinear situations with respect to which the battery may get degraded, right? What if my monitoring software, which is sitting in my cloud, collects all of this data, synthesizes what I should do to make it more optimal, what I should do to make it more livable for a longer period with respect to the state of health, right? It happens at that level in the cloud, and then with that data that I have and the logical information that I have, I will be able to let my vehicle know, the physical vehicle know through my IoT, hey, don't charge it, wait for some time. Because anyway, customer is going to take that bike in the morning, 7 o'clock. The moment you connect the charger, don't charge the vehicle. Maybe just do it at a slow charging rate, and then maybe do the full charge by in the morning in place before like 3 o'clock or 4 o'clock to morning, 7 o'clock. So like when you do that, you can possibly enhance the life of the battery, because that's what every company is betting things behind. They sell the bike, they tell it is 8 years warranty. If the battery goes out of the warranty by 7th year, you're getting a battery which is going to cost a lot of money for them, repairing them or doing whatever it is. So the solution of digital twinning is just a one example case, which I'm able to give you, that I'm trying to protect my battery's life with the help of data that I have from the physical component. I'm trying to compute this at my simulation level, and then do a lot of stuff that helps my battery to extend its life. Apart from this, now, if you're developing a next generation vehicle, right? Imagine Tata launched their Nexon in 2015, 16, 17, something like that. If you have this data, you can really tell the machine learning models, develop AI models, to develop a new vehicle platform, to develop a new battery. Hey, what should I take care of? What should I focus upon to make my battery more reliable, safe, or also have a better longevity in place, right? So I can do a lot of diagnostics, prognosis. I can tell my problems earlier. I can probe my problems with the help of data and all of that. So my service becomes very easy, right? My repair becomes very easy. My repair costs become very reduced. And that's what people are talking about called complete twinning. The whole thing with the data coming from the physical system to the cloud, and then say, do all of these computations, come up with something that makes life better, right? And that's just what I realized myself in the industry of digital twinning for the batteries. Cool. That word of digital twinning is there in every different industry. It is for different meanings, but for the battery industry, that's what we call it as digital twinning of batteries. You need the models, that's the fundamental layer. Then you need the cloud and computation and blah, blah, blah stuff, logics, AI, ML, and everything that makes it all possible as a model to work it in the cloud. Any questions from anyone? Okay, if you have questions, feel free to draw those questions in the chat box. Great. I see our teammate Vinayak has dropped the messages, in case you guys would like to join a group of WhatsApp where you get updates about what we do. You can also be a part of that. Cool. With that note, let me move ahead. So Krishna spoken about this, that there are type of models, type of softwares, all of these things that exist in the world today to make these models, right? And then finally, if you want to be in this sector, right, which I greatly see as a challenge, is that the people who have deep knowledge of chemistry may not have an exposure to mathematics and modeling. People who have a great knowledge, like engineers like us, who have a good knowledge of mathematics and physics and modeling, we do not know chemistry to that level, right? Because when Krishna was talking about it, and also when Dr. Manjal was talking about it, we talked about chemistry, a lot about chemistry, and also bits and pieces about the modeling. If you want to model it, you're modeling the battery, right? You're modeling the complex component. If you don't know what is the battery, what is the chemistry behind it, when I apply a voltage, if the voltage increasing, what's really happening at my, at a part level of an ion, right? What is all it is changing inside a cell to behave it like that, right? It's a very complex thing. So somebody to understand chemistry, somebody to understand the mathematics, somebody to understand the physics, somebody to understand the modeling softwares, the modeling tools, the modeling methodologies, all of that. And then finally, somebody also need to understand the cloud, connectivity, the AI, ML, all of these things. The finally derives into the complete product. But as an individual person, you would not be able to do everything, right? You would not be able to do everything because it's so much vast of its own nature. So you have different type of job roles in the industry, like material engineers, cell design engineers. The material engineer is purely a material scientist, right? And the design engineer is a combination of mechanical, electrical, electrochemical, chemical, all of that. Then the manufacturing engineer, who is so good at understanding how a large scale system works. How do you control the manufacturing? How do you control the quality? How do you control the repeatability? All of that things and understand process controls, feasibilities, control systems in manufacturing, setting up of plants, controlling any quality issues in the plants and things like that. Then we have test engineers who understands how do I make sure this doesn't go bad, right? He or she can test them in variety of patterns and fashions in place. Not only when the cell is made, no. Even how do you form a small material package to go to take it for XRD? There's a lot of time and efforts to even prepare a sample to test under an XRD or an SEM or anything like that. There's a lot of efforts to prepare a material even to perform any of the CV or cyclic voltammetry or GITT or any of those tests in place, right? So all of that, and then finally a cell, and then testing a cell, the module, testing the module, battery, testing the battery, and then making it a life of the data in place to make an engineer to work on AI and ML. That's our testing engineers. And then the simulation and modeling guys who really work on mathematics, who work on equations, who work on softwares, tools, writing the programs and things like that to work their real life to develop the digital models. And then finally, our application engineers who understands where my battery is going to be used. He understands that the application perspective of a cell or a battery, he can suggest, hey, I have 5 products and this is the right one that suits to your application. So, he really have a proper exposure to how to work with cells to an application perspective of it. So now you know what is the life of a battery from the journey to journey. And now finally, you end up wanting to be an engineer in a specific area, right? So if you want to pick it up, you require a real experience. Today, we have companies in India who are making cells. That's the fantastic thing that is happening. Today, we have companies like Agartha has come up. Reliance has invested in India. Tata's have invested in India. Even the players like Ola has invested. I have come across a company called Nash Energy, Godi Energy. All of them are investing heavily to manufacture cells in India. And there may be many of other companies as well. Also, there is about recycling, right? Because government has made it mandatory that if you are a battery manufacturer, if you are an OEM, you need to have a recycling plan as well. That means you cannot just dump those batteries into the environment and the lakes or, landfills. So how do you recycle them? That is also a huge, complex chemical processes, right? We need to have exposure. We need to have experience to build the career in this industry or to carry out research in this industry, right? So where do you gather all of this? How do you intend it to build? I'm sure maybe at overbet, I would also say that I have not come across any university in the country who offers this exposure at a one point to the person who want to learn, right? I have not seen even in any other places also that you can pick up everything, have theoretical classes, maybe at a one scale, but also having a lab where you can really learn things, because teaching something on the practicals and theory and it's beautiful, right? But you don't really get a hands-on experience of doing something. And that's what industry is asking you for, right? So it's just something I see as a need for the industry, that it requires a lot of people for this sector, but there are not of people available because there is not a good enough ecosystem available in the academics that to teach these things. Second thing, to teach these things from the perspective of an engineering to an application is a very different thing. So that is something that I realized in my whole life of 5 years working with batteries, that I wanted to bring out a course which is very, very meaningful, which is really, really hands-on oriented, and that makes somebody prepared for the industry to get into. And that course is called as the Master Certification course in Battery Materials, Characterization, and Digital Twins. This course is overall effort of 4 to 5 years of our learning, working with the battery industry, and cumulative experiences of people like Dr. Manjunath and Krishna and Abhinav and our own team sitting here in the lab to gain experience and build a course that can help people in the sector of battery materials or the industry to get into software twinning, so that you can pick up your skills to become a great engineers for the sector tomorrow. So this is a quick overview of the course, which I would like to just bring it out so that I can, make sure wind up this session in other few minutes for all of you. Yeah. So this course that we currently have is called Battery Materials and Digital Twinning. Okay. With the help of this course, then the screen sharing might have worked. Okay. All right. Not sure if that is still working. Okay. So we have developed this course that is called Master Certification course in Battery Materials and Digital Twinning. This is the same course Dr. Manjunath was also introducing as a part of this program. It is about a 1 year long course, highly focused for people who want to work in the battery industry, and highly focused to the broad spectrum of everything in batteries. So there are multiple modules as a part of this course. It starts with understanding chemistry, specifically not just a chemistry in general, but electrochemistry as a specifically point of it. And then the materials and components of the batteries, key characterization techniques. We spoke about varieties of characterization techniques such as EIS, cyclic voltammetry, GITT, and varieties of characterization techniques, physical techniques. Also has the lab where you can actually come and conduct an experiment and develop the materials themselves. Okay, so where you will be able to practically create an anode and cathode and get an experience of how to develop them, And these photos are not taken from anywhere else in the world. This is our lab present in Bangalore today. And then you perform variety of testing and characterization activities. Again, the lab visit where you will be able to collect your own data, and by conducting tests, then you learn how to create models, which is RC models. Then, working with EIS, practical test facilities. The test facilities are within our lab today in Bangalore. You get an access to the lab and then conduct experiments, collect data. We also gather a lot of data that we can give it to you in terms of developing the models and learning through them. And then finally, creating electrochemical models, okay? And then making you to become more industry ready to get into the sectors of energy storage or automotive or battery manufacturing in place. So that's a quick note about there is a course that can help you if you want to become a specialist in that specific area. So with that note, I thank you for attending this session. So I try to make sure to keep it as close as possible to 1 hour. So it's about 6:52 right now. So if any questions are there, we have a few more minutes till 7. We can take those questions and have a chit chat if you have any queries. Over to you for any questions, please. Okay, any questions from anyone?
Hello,
Hello. Hi, Darshan.
is my voice audible?
Yeah. Well, please.
I'm also actually I am in a battery industry as of now, but there are some things which I'm inspecting in raw materials. Actually, I'm into inspection of raw materials,
Mhm.
and there are some properties like particle size, surface area, and oil absorption, which goes take,
Right.
which is taken care before providing material to the production team. Okay, so I didn't found all of those terms in this while we are discussing of particle science of cathode and anode materials. So this is also involved in what you have study material that you are giving while you said the course that you have developed. Yeah. Yeah.
So certainly, it is there as a part of the course, specifically on characterization. We have the module which talks and also gives you a good introduction about variety of approaches to do the XRD, SEM, all of these things. So we will be able to study the variety of structures or material compositions and all of that as a part of the course, apart from physical testing of half electrode or a full cell with a different variety of tests.
And that part that you said was quite amazing regarding that individual functionalities of materials, because lithium is not only the one material that works in getting batteries. So, okay, that is one that I found quite insightful. Right?
Sure, sure. Great. Fantastic. So anybody, yeah, Ashish, yeah, please, over to you. You have a question.
Sir, I don't have a question, but I just want to communicate.
Sure.
I was associated with Decibels, and it was a fantastic journey. Friends, I would like to just mention my regards. That facility at Decibel is really nice. Labs, cell facility, motor facility, everything, and what I got the all hands-on experience. Okay, so that's I want to communicate, and faculty is very very nice and best in world. Thank you, sir.
Thank you very much, Ashish. Thanks a lot for the comments.
Excuse me.
Yep. Hi, Suraj.
Sir, this is Chandrabhushan, Suraj Sibi father.
All right. Hi.
I was not in a session, but I am also into research, academic research, but not in this field.
Okay.
So Suraj right now he is pursuing his diploma in computer science.
Mhm.
He is in final year.
Okay.
So he having colleges 9 to 4 o'clock regular. So actually, I wanted to him associate with the complete formal program what is being offered by your organization.
Right, right,
So keeping this his class into the mind,
right.
I just want input from your side or your organization, how he can join systematically from very basic to the next ladder like that, in spite of committing all at a time.
Yeah.
Because after diploma, he has to get enrolled in engineering. But at the same time, I personally realize that the exposure what your organization is giving is quite valuable and rare, at least now.
Right.
So I need your help in that regard. My mail ID is there. If you could help me in that direction.
Sure, sure, sure. Just to throw a quick light, it at least requires about 10 hours a week for someone to practice. So
Okay.
that's the important thing. If he has about 30 to 40 hours a month, that's about a 1 hour a day nearly, right?
Okay.
So he can possibly put an efforts to get through the course because the course has a lot of self-paced learning content. So if he can have that 1 or 2 hours in a day to spare, he can definitely take it up. So that's the only input I can give. If he has that time, you can help him to take through the course.
Yeah. So is it possible that I send him one day to your institution and where?
Yeah. Yeah, we can do that. We can do that. Vinayak, I think we have collected an email ID. So we have the email ID. Possible.
You use the email ID, no?
Sure. So we can drop an email to me and Vinayak. We will arrange the option to have this visit to the lab.
Okay, sir. Okay, sir. Thank you. Thank you very much, sir. You have taken sir's email ID. Sir, can I have your email ID?
Yeah. So it is in the chat box. I'll retype. Vinayak, you can retype the email ID, please.
Please look out.
Yeah. Okay. Vinayak can also make the note of the email ID. Yes. Great. Thanks for it. Thanks for it. It's a great concern about your son. Thank you very much.
Thank you, sir. Thank you.
Okay. So anybody have any technical queries that we can address? Okay. So that's great. And thanks a lot for everyone for being part of this event.
Hello, there's one point from my
Internet. Over to you.
Actually, my team consists of from 3-4 members, and what I was looking at is somewhat more deep knowledge on this raw material related inspections or somewhat like that. Can I get something tailored in that form so that I can provide this training to the team members?
All right. All right.
Team which I
Sure. I think we can connect on that, Darshan. So you have our email IDs, and we may also have your email IDs. Let us connect. So I can see part of the course is suitable for you. Not everything, I think, for your company requirements.
Yes.
We can work it out in that way. That's the best thing. Maybe break up a few modules and then that suits to it. But when it's to a specific industry, we may have to develop something upon what exactly you are using and things like that. But we can work it out more. Let's have a catch up on the email or things like that, and then we can continue our conversations.
Sure.
Okay. Thank you.
Okay.
So, yes, we have anybody else for the questions, please?
Yes, may I raise one question?
Yes, please.
Yeah, my name is Amari. Are you listening me?
Yes, it's already.
Okay, I'm from Ethiopia, Addis Ababa University PhD student. So yeah, and I'm working on lithium-ion battery, and I've been working on lithium-ion battery with liquid electrolytes. And as you know that, actually, firstly, your laboratory design, the course design, just is very interesting, and I'm very happy what I'm seeing on the screen.
Right.
And now here my comments or question might be. You know that the liquid electrolyte battery is almost reaching some limit in terms of energy density, about 300 or 400, something like the maximum of that much.
That's true.
And moreover, is facing explosion issue
Correct.
and dendrite formation at large. And fast charging issues are still some of the burning issue with battery with liquid electrolyte.
Yes.
And because of this, scientists or researchers, may I say, are shifting toward the solid state batteries.
Yes.
Just currently, more focus is being given to the solid state battery.
Yes.
And just I'm saying the design, everything is very interesting. And my question here is, in between, I try to identify which electrolyte are you using, and I hope your partner answered the question liquid electrolyte. But currently, just there is a shift toward this solid electrolyte battery because of it is higher energy density, and the dendrite formation would be a little bit minimum. But still, the compatibility issue is there because of solid-solid interaction. It's it can be operated. Solid state battery can be operated at higher temperature, and it can store a large amount of energy, and mean that high energy density it has that. And because of this, are you going to include the so-called solid state battery as part of your study or something like that? Is that
Interesting.
really, if I get the chance and join the course and complete the course, I would be happy. And but studying the solid state battery inclusively needs more focus, and in line with this, how you are planning, I don't know. I want to listen from you, and thank you very much.
Absolutely. Morgan, it's really great to hear from you, and you have already an experience working with the batteries. We have a part of the module which focuses on solid electrolyte, and the second important thing is that Dr. Manjunath has developed some of the solid electrolyte materials because he's a material scientist by himself, and a ceramic-oriented materials which are able to hold a very good temperature, very solid level, compatibility. So certainly, on a broader note, we have a part of the course which is focuses on solid electrolyte batteries. Specified interactions can be made through, and that can be built up as a part of the engagement. The modeling of the solid electrolyte is possibly not taken care right now, to be very frank and honest. I can check with Krishna if we have that possibilities to take care of modeling in the solid electrolyte in the course, and we will look forward to have those discussions to make it more effective and progressive.
All right, just to include some more information, if possible.
Yep.
Yeah, okay. There is a project with an Italian university, the LUT University, I don't know if you are familiar with. And different universities and industries are studying this solid state battery, or the battery as a whole being combined together. Is that the PhD students and the university as well as the industry? That and I have been one of the PhD students who has been participating within that course and project work. Right now, I'm doing a project work. I have already completed, I may say I have completed my PhD in DCIR University. And in line with my PhD, I've been taking project work, a course in project work, is that in Italy, being in Ethiopia, but through online course, I've been taking that. And right now I'm running the project work, is that?
Okay.
And they are working on solid state battery widely, that, and if you make it part of your study, it would be more attractive, I hope. And still, your design is very nice, and thank you much.
Thank you very much for your time and efforts to participate and also interact with us today. Thank you so much. Right. So amazing to hear the participants and the variety of backgrounds. So anybody else, like we passed 7, any quick questions from anyone at last? And that should be good to go for today's webinar if you're done. Okay, so pretty much I think we got an input from everyone and the questions and interactions to make. Thank you very much, everyone, for being part of today's webinar. It's amazing and enthusiastic for me to create something and make it beneficial for many people to build their career on top of it. And I look forward to see this course benefiting to all of you and to the whole industry and to the clean energy movement, to the batteries that we can make in the world. Thank you very much for everyone. And thank you, Dr. Manjunath and Mr. Krishna for helping us in joining to the sessions. I'll pull them in for fantastic sessions in the upcoming future to talk about in depth of these topics. Look forward to meet all of you again in the future. Thank you very much. Good night to all of you. Bye-bye.